All right, here we are with example 4 of section 6.2. Here's another one of these described solids. Find the volume of the solid whose base is the quarter circle of radius 1 in the first quadrant. So let's go ahead and draw our coordinate system. Let's just focus on the first quadrant. And it is the quarter circle of radius 1. So it's just the upper right half of the unit circle. Let's see if I can... For some reason, it's always easier for me to draw my circles like that. Okay. Not perfect, but it's okay. We don't have to be. So this is 1 and this is 1. It tells us then that this is the base. So then cross-sections perpendicular to the x-axis are squares. So I'm going to draw a representative slice at some arbitrary x value between 0 and 1. And then this is the side of a square. The square comes out of the screen or out of the page. Okay? So what I can do here is imagine drawing this square. So if we focus on this square, again, that looks like a terrible square, but whatever. So then this distance here, the length of this side length, if we're at some x value x, what is this side length? Well, it depends on what this y value is here, which depends on what this curve is. Since this is part of the unit circle, we know that the equation of the unit circle is x squared plus y squared equals 1. Okay? Okay. So this distance here would be the y value. So we'd solve this for y, and this would be technically plus or minus the square root of 1 minus x squared. But since we're doing not the full unit circle, but just the half of the top half, we would want the positive root because we are looking at a portion of the top semicircle. So we'll just take a look at that. So this square has a side length of the square root of 1 minus x squared. So that means the area of the square, A, is, well, it's a square, so side length squared. So this is 1 minus x squared. So the area as a function of x is 1 minus x squared. So now we are going to be integrating with respect to x, much like we did in example 3, the previous video. In that video, I drew what this solid looks like in 3D, and I will very, very, very quickly do the same thing, but I'll show you how I'm thinking about it. So I'm going to just draw my 3 space axes, which this is x. So the xy plane is actually the base, it's the bottom, and then this z-axis goes upward. So in this perspective, the z-axis would be coming out of the screen towards you. And then I'll draw this semicircular arc. So this would look something like maybe a little bit more. Not great, but with a little bit of perspective, that's what it looks like, more or less. And then here we want to pick some x value between 0 and 1. So let's just say right here. So there's some x value. And then this, I want to make this parallel to the y-axis. There we go. This is going to be a square. So the square should be a little bit taller, like that. So that's what that cross-section looks like. And this side length here is just square root of 1 minus x squared. So if we picked a different side length, let's say right here, at this x value, the side length is a little bit different. Oops. There we go. So that's what it, ultimately that's what it looks like. And these squares, of course, will shrink the more we get closer to the bottom here. So for instance, one of them will be like this. And of course, they'll get even smaller than that. Okay, so that's what it looks like in 3D. So you can see that the squares are the squares are varying size as we move in the x direction. Whether we go from 0 to 1, they start off large here, a square that has a side length 1 by 1. So this is a square with area 1 unit squared, whatever units of measurement we're using, say meters. And then as we move this way, the area is going to decrease. So everything's changing as we move in the x direction, which is a signal to us that x is our variable of integration. Okay, so the volume would be the integral of that cross-sectional area. So from 0 to 1, and then our area, 1 minus x squared dx. So this is x minus a third x cubed between 0 and 1, which is 1 minus a third, which is 2/3. And then whatever units we're using, I'm just going to assume meters. So this will be meters cubed because it's a volume.